Hey guys, today we're going to talk about galactic astronomy. That's everything that's outside of the solar system. Last time we talked about stars and the sun and planets and moons and comets and asteroids and all of that stuff. That is very close to to planet Earth. Um, Today we want to talk about everything that's out beyond that the stars and the galaxies and everything that's not in our local neighborhood, so to speak. When you look up at the night sky, you'll see something that looks kind of like this. That band that runs across the middle, all of these stars in here are called the Milky Way galaxy. And the Milky Way galaxy is a big collection of stars that are close to us somewhat. And there's something like 100 billion to 400 billion. And but the this band running across here that you see, hundreds and hundreds, thousands, millions, billions of stars right there. We are in that flat disk of stars that are spinning around. Everything out here is somewhere else, something else. And honestly, it may not even be a star. It may be galaxies and galactic clusters and nebula and all sorts of things that I wanted to talk about today. So lots of stuff out there, and let's see what we've got. Here's a picture that I thought would be interesting. This is what we talked about last time, the solar system here, a star in the center, a bunch of planets. Everything spins in a flat disk. This is what a galaxy might look like here. Instead of one star in the center and everything going around it, it's just a big disk of stars. The pattern is the same though. Here, whether we start with a planet, and it could have rings, it could have moons, and they're all spinning in a flat disk. Planet in the center, but flat disk around it. The sun in the middle with a flat disk around it, planets, comets, meteors, all of that stuff. Or the galaxy, a big flat disk of stars. So I find that symmetry, that similarity in the shape of these things telling. Of course, it has something to do with how all of this formed. And cosmology is the branch of science that looks into all of that. But that's pretty interesting. Now, if we've got a planet that's at the middle of a planetary system, and if we've got a sun that's in the middle of a solar system, what's in the middle of a galaxy here? Well, 30 years ago when I was in school, you couldn't definitively answer that question, but it was speculated even back then that black holes were the thing at the center that had enough mass, enough gravity to hold all of that stuff spinning in a circle. Today, we can see ejecta here with the ejection from the black hole. There's an accretion disk around here. So all these kind of things that we'll be talking more about, but it's the same kind of thing, and it builds up stars and planets. It just kind of sucks everything up there by gravity, and eventually it consumes that. And when it does, it releases a good bit of energy. But you can't see the black hole. That's why it's called black, because it doesn't show up. It's a ball that's so massive, that's so dense, that it sucks everything in eventually, even light. And so light can't escape from there. And if the light can't hit and bounce off and come back to us, then it's going to be invisible. It's going to be a black hole. And you can kind of see that right there. But it's interesting that pattern repeats so many times there. Our galaxy, again, is called the Milky Way galaxy. We don't really know how many stars there are. You see numbers anywhere from 100 to 400 billion stars. That might be on the low side, might be on the high side, but I don't think so. It's a lot of stars. The difficulty, again, is that we are in the disk. We're way out here on the frontier of this thing, and we're looking through the disk. So it'd be kind of like standing in a forest and saying, well, how many trees are there? And you can't see beyond the first 3 or 4 rows of trees. So, it's really kind of hard to count when you're standing there in that. But that's that band that it showed here, you know. So how many stars are right there? Not counting the ones that are even farther back behind. It's hard to say. But I'm putting something like 400 billion on here, a whole bunch of them. It's about 100,000 light years across. A light year is the distance that light travels in 1 year. So if you started here on one side of the Milky Way galaxy, it would take you 100,000 light years. It would take you 100,000 years to go all the way across if you were traveling at the speed of light. And we can't go anywhere near the speed of light. All right, we can, barely break the speed of sound, and the speed of light's like 10,000 times faster than that or something. So, it would take a long, long time to do. We are 30,000 light years from the center. So if it's 100,000 light years all the way across, it'd be about 50,000 light years to the edge, and we're about 3/5 of that way. So the little arrow here, you are here, is kind of a little ha-ha joke, but we're somewhere out there on the frontier, out in the sticks, if you will, of the Milky Way galaxy. That's a good thing, actually. Can you see how concentrated everything is in here? We don't really need to be in that much traffic, so Columbia is bad enough. But that's what we're talking about when we say a galaxy. It would look something like this. This is called a spiral galaxy. See how the arm kind of spirals off? And there's a second arm right here. This specifically is a barred spiral galaxy. It's got that bar going across the center. Some galaxies have that, some don't. I've got a picture coming up about that. Obviously, this is not a picture of our galaxy because we're in that galaxy. This is a picture of a different galaxy, but you get the idea. Ours is going to look something like that, and we see these things with telescopes. You don't even have to have a super great telescope to be able to see galaxies and to resolve some of those bands and arms like you see there. It takes us about 200 million years to go around the center. This whole thing is spin, I guess, actually going this way, but as that thing spins, that's one more kind of motion. We talked about how the Earth rotated on its axis every 24 hours, how it spins around the sun, how it rotates around the sun, or revolves around the sun every year, and how it's got that little 26,000 wobble. Well, every 200 million years, you make a complete trip around like that. So that's one more kind of motion in the universe that we have to think about sometimes. The Milky Way, here's another picture looking up at the Milky Way galaxy. You can see this in the night sky, but you do need to get away from lights, away from cities, away from car, all of that stuff we call light pollution, street signs and not street signs, but billboards and street lights and stuff. If you go way out in the country, you can look up in the night sky and see the Milky Way galaxy, and it is like a little milky glow, just in that band of where our galaxy lies. So next time you're out in the country, check that out. Okay, all of these stars, the something 100 billion stars in our Milky Way galaxy, and the stars beyond that. There's lots of things that we like to measure about those stars. We're trying to understand A, how they work, B, how big they each are, and how hot they are, and what color they are. Well, that's tied up with the temperature, and you can, even in this little picture here, you can see some yellow stars and some blue stars and some, right there's a little blue star and yellow stars. There's green stars and all kind of colors, okay? Again, that has to do with their temperature, and I got a graph coming up on that. But here are some numbers that we measure. The luminosity is how much light the star actually puts out. And the apparent magnitude is how bright it appears from Earth, while the absolute magnitude is a brightness from a fixed distance away. So this is kind of like if you took a bright flashlight and you held it in your eye, it would be really, really bright. But if you had your friend hold it across the yard or across the football field or something, it wouldn't be nearly as bright. So that's the same thing here. Some of these stars are brighter than others because they put out more light. They have more fusion going on, hydrogen being converted into helium, and they physically put out more light. Some of them appear brighter because they are closer to us. So we always have both of those things going on there. And these numbers kind of measure that. How much light the star actually puts out, how bright it looks from Earth, and how bright it appears to be from this distance, 10 parsecs or 33 light years, or that many kilometers away. Okay, so that's worth knowing about. Here's another way we learn about stars right here. These are referred to as spectral lines. If you look at the rainbow, if you pass light through a prism, like you see here, or a diffraction grating, it will separate the light up into the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. And so that's what you see. Here's a star. The light from that star comes. We're looking at it with a special telescope. It's all closed in and stuff, not like the picture here. But that light passes through a prism, and it separates that light into the rainbow. The only thing is, there's sections that are missing of this thing. There are lines, there are gaps in it. And we refer to that as the spectral lines. You can look at those lines and where they are and identify the gases that star is made of. Now, most stars are principally hydrogen, right? So you're going to see these lines right there in all that starlight, okay? But you might also have helium, and measuring how much helium there is tells you a lot about how long hydrogen has been converted into helium. So if there's a lot of helium, then you're looking at an older star or a second or third generation star, one that's already lived a life as a star, exploded, and then that gas was recollected, and so there's more helium that it builds. Fusion continues and builds heavier and heavier atoms, and so you can look for these other things, iron and calcium, magnesium, but that's where all of this stuff came from. It came from the furnace of the sun and the furnace of all of these stars that are taking hydrogen, the smallest, simplest, lightest element, and fusing it into bigger and heavier things. The graph on the side here could be from different stars. This would be the light signature from a particular star, and then here's a different one. And you see all of these stacked up here, and they're going to have different spectral lines and different places where they do that. The temperature makes a huge difference. The temperature is not marked on this one. They're talking about the flux, how bright it is, and the wavelength, which lines you see. But a hotter star is going to emit energy in the ultraviolet, and then you've got the visible range and the infrared range, and so I guess it's ultraviolet, blue, I thought that was visible, but that wouldn't be blue, would it? I don't know what this, I found this somewhere. And then the red and the infrared. So that's probably infrared and ultraviolet here in the visible there. So there's a lot of energy, a lot of radiation coming off of these stars. And looking at these spectral lines is one way to really nail down what's going on inside that star. If you take all of that information, the magnitude of the star, how bright it appears to be, the surface temperature of the star, again, the color is a really good indication of the temperature. You've turned the stove eye on, right, to make some soup or something, and you look over at the stove and it's hot. It's just glowing red, and you say, oh, it got red. It's good and hot. I certainly don't want to put my hand on it, but it's ready to heat up some soup. So right here, your red stars are here. That's about 2,500 degrees Kelvin. A little different temperature scale there, but at these temperatures, it doesn't make a whole lot of difference. So here's your red stars. They're hot, but the yellow stars are even hotter. And then it goes into straw and blue, and you've got all these colors here. This band right there is called the main sequence. And stars live most of their life on this main sequence. You can see that there's little stars and there's big stars, right? Some of these guys are pretty small, and it doesn't really matter what color. There's blue little stars and yellow little stars, red little stars. There's also big monster red ones and yellow ones and blue ones. For reference, our sun is this guy right here, okay? He's marked that. There's nothing particularly amazing about our sun. It's not big. It's not the smallest star. It's not the biggest star by any stretch of the imagination. It's not particularly bright or dim. It's a yellow star, meaning that the visible light that it puts off mostly is a nice yellow color. That's nice. But there's nothing really special about it. This shows how all the other stars, not all of them, but a bunch of them stack up, and the sun's there just kind of for reference as one of these main sequence stars. All right? These O, B, A, F, J, G, K, M letters across here tell astronomers something about the kind of star and the color and the temperature and all of that. We don't need to go in that deep. But I've got a picture here that shows what happens with stars, and then we'll go back to that other diagram and kind of see what happens. So stars are made of gas. Here is a big cloud of gas. We call that a nebula, and which literally means cloud. All right? That cloud of gas has mass, so gravity is working in there, and it's gathering that, and over, let's say, millions of years, it pulls that gas together. It's going to shrink that cloud down and compact it. And as it does that, it begins to spin. You could think about, if I start grabbing friends in the hallway or something, we could all spin, and it's not quite like that. Gravity is doing the job here, but they're little bitty lightweight things. As they move together, they kind of swirl like that and make what we call a protostar. And as they bunch up, you can see that there in the center is a little hot spot where that gas is beginning to fuse and emit some radiation there. As it continues to pack down, it becomes a proper star. Okay? So that's kind of where our sun is right now. And you've got hydrogen fusing into helium. That gives off the light and the heat and the energy that we need to stay alive. When that hydrogen begins to be depleted, when we start to run out of hydrogen, then that star is actually going to swell up. Now, you've always got two things going on. You've got gravity trying to pull it together, and you've got this radiation, this nuclear fusion bomb going off in the core that's trying to blow it out. And so those two are always kind of battling here. But when it swells up, it could be either a red giant or a supergiant right there, depending on how much mass the star started out with. A more massive star would turn into a supergiant, and a smaller star like the sun would turn into a red giant right there. It's projected that in millions of years, when our sun reaches this point, that this thing is going to swell up well past the Earth. So that red giant's going to kind of come out, and the Earth will actually be, down inside the sun, be consumed by the sun, if you will. And then you can have a nova here, where the star explodes. There will be a little core left behind, and as that condenses, shrinks, and cools off, it becomes a white dwarf, kind of a little dim, faint star, kind of like a campfire that's burning out, It's lost all that energy and heat and stuff, but there's still something left. As it cools off, it becomes a black dwarf, like that. Black because it's not putting off light anymore, right? So that's kind of the cycle of our sun. Gas was collected, spins up, gathers by gravity into a ball. It's going to swell up, make a red giant. It'll explode and the core left behind. All of this gas right here gets cast out into space, and that gas will then be regathered together, make a new nebula, could become a new protostar, could become a new star, and you can go through this cycle multiple times right here with the same materials. And that's part of how those heavier atoms get made, is because they've been through so many generations of this thing. The supergiant over here also can explode. That's called a supernova. Nova actually means new, like a new star. So a long time ago, they would look up in the night sky and they would see a star that they hadn't noticed before, because there was this really bright light in the sky. Really bright's kind of relative, but you know, it would show up in the night sky. Some of the supernovas they recorded, you could actually see them during the day. There was one called Kepler's supernova about 400 years ago, and the reports say that you could see that during the day even. Maybe I wasn't there, but these you know, they called them, hey, there's a new star being born. Well, no, it's actually an old star that was dying, that was exploding, and but we still use the word nova and supernova for these things. There will be a core left behind right there. It could become a pulsar, which is a spinning core of a star that emits radiation, and we see this little beep, beep, beep as those pulses of energy reaches. It's almost like a lighthouse spinning around, and we see that signal. If there's enough mass, it could become a black hole, and it could start to gather more stars around it, and as it eats those and gains mass, then you could get a galaxy there. It just depends on how much stuff there is around you to be gathered up. But it's that cycle from clouds of gas into a star, explosion, the gas goes back into the nebula, could go around again. You get these little cores, white dwarfs, black holes, pulsars that are kind of left behind doing their thing. So that's the lifetime. Now back here, when we were talking about this thing, this is called the Hertzsprung-Russell diagram, or the HR diagram. There were two guys, Hertzsprung and Russell. They were both astronomers. They both drew this graph, and so we kind of give both of them credit. They had different axes and stuff, but that doesn't really matter. You're looking at how bright the star is. You're looking at the temperature. You're looking at the absolute magnitude, how bright that appears to be. You can see that as the luminosity goes up, the magnitude is also going to go up. Now, when I say up, the number goes down. It's a kind of backwards, weird scale. Don't worry about the numbers, okay? But the temperature is kind of driving both of those. Almost all of those stars that are, you know, established up to middle-aged stars are kind of in this band, the main sequence. When they start to become senior citizens and swell into red giants and supergiants, you know, they're up here, okay? They've cooled off, so they're not as hot as the stars over here. They're down around 2,500 instead of 20,000, you know? So these guys are cooler than the other side. They've swollen up. The giants and supergiants are over there. Down in this region, you've got all those white dwarfs and black dwarfs left behind. So, you know, this chart is just kind of a nice way to put all the stars on one thing, line them all up, and see how they compare to each other, like that HR diagram kind of shows that. Now, astronomers, people have been looking in the sky forever, right? And they've been making up stories, and they've been attaching them to local legends and myths and whatnot. Around 1600-ish, they started making telescopes. And with the advent of telescopes, last time we talked about how Galileo could see the moons of Jupiter, and all of a sudden here were things that were going around a planet which flew in the face of the idea that Earth was at the center and everything went around the Earth, right? Well, this guy was looking for comets. Charles Messier, Frenchman, in 1774 was really interested in comets, And so he had a telescope and he's looking around trying to find comets and write them all down. And he keeps finding these things. He goes, I don't think that's a star. I don't think that's certainly not a comet. And so he kind of made a table of them, a list of objects. And we still use this table. These might be, I think this is M2 or M4, meaning that it's the second thing on Messier's table, right? And M37 and he found initially 45 objects that he didn't know what they were, and then it expanded to 103, and I think it's at 110 now. Well, we know what they are today. They are these kind of things here. It could be a spiral galaxy. He's looking through his telescope and he sees something that looks like this. Probably not that good of a picture. And he says, I don't think that's a single star. Well, he's right. It's 100 billion stars. Right? It's a galaxy. It's a whole nother set of stars like the one that we live in. And that's pretty interesting. Here's an elliptical galaxy. It's a whole bunch of stars in a ball, in an egg shape. Okay? But they're really close together. So it's not a flat disk like this. It's more of a sphere, an egg-shaped thing. A globular cluster is similar to that, where you have a cluster of galaxies, and all of these galaxies are formed together in that ball right there. Or you could have an open cluster where there are galaxies kind of sprinkled around. They're not gathered up into a ball like that. And of course, some of the things that he saw were nebulas, clouds of gas. And I've got some more pictures of nebulas coming up. But it's hard to see anything in the universe that's not beautiful, honestly, except for where people have messed it up. Beautiful country road, and people are going to throw beer cans out the road and stuff. It's just, that's what we do best, I guess. But when you look out in the night sky, there's just so many beautiful things out there. Some of these aren't particularly good pictures, but some of these things, sparkle like diamonds on a piece of black velvet or something. They're just incredible. And the nebulas probably are the best of all of them. And I've got, like I said, some more pictures right now. Here are some nebulas. They all have names that have to do with their shape and what they do. This is the Butterfly Nebula, and this is the Horsehead Nebula. I think this is the Cat's Eye Nebula, and the Pillars of Creation. Here you can see that there's a lot of this gas out in the background, and then all of this cosmic dust and other stuff is kind of blocking some of that. So that's kind of an interesting thing. But these nebulas are stars that are, exploded, or they are clouds of gas that are being gathered together. So, right there at the core of this guy, you can see a little red star right there, and here's a cloud of gas going around on the outside. That's a star that's exploded. You could see this as a star that's exploded. All of these things, maybe not this one, right? And when you look at, I believe this is the one in the constellation Orion, and when you zoom in on that, you can actually see a star nursery where new stars are being gathered and born, second, third and 15th generation stars, little baby stars being born. So it's pretty cute. It's the death of a star, but it's the new life of a star. As one thing ends, the next one begins, and the universe likes to do that. Let's talk a little bit about galaxies. Down in the bottom is a little animation of this thing spinning around, and that's kind of what you have there. Again, you've got a black hole in the center that has enough mass, enough gravity to hold all of that stuff and to pull it, just like the sun pulls Earth around in a circle. And it's the same physics on that. Right here you see some different shapes. Here are two galaxies close together. They're having a little dance right there. They're actually seeing who's going to win. And you got mass here and mass there. That's gravitationally attracted, and those will merge and become one galaxy at some point. Right here you see a barred galaxy. Probably started with a couple galaxies that got combined, and you've got sweeps of stars out here on the side. All of those stars could have planets. We're finding more and more exoplanets like we talked about on last time, you know. So every time you see a star, think, well, gee, could be a planet, could be moons, could be clouds, could be creatures, right? It's not impossible. When I was in school, nobody knew about any planets that existed outside of the solar system. Now we've got a pretty big list I've got coming up. What else is out there? We don't know yet. That's what we're trying to find out. Edwin Hubble, you've heard of the Hubble telescope. He was an astronomer, and he was interested in galaxies, so he made the elliptical galaxies, E0357, talking about how elliptical, how flattened that circle was. S was a spherical galaxy. Here you had the spirals going this way and this way. These guys have bars, so see how that's a barred spiral galaxy? And that's kind of an extreme case of it. These do not have bars. It's just kind of a flat disk spinning around, just traditional spiral galaxy. So these things can take lots of different shapes depending on, you know, what they had for lunch. If they've eaten another galaxy and assimilated those stars by gravity, then, you know, that's going to influence what the thing looks like. There's a lot of stuff out there. Here's just some rough numbers. If our galaxy has something like 400 billion stars, and there are something like 2 trillion galaxies, then that's 8 times 10 to the 23 stars. That's an 8 with 23 zeros after it of stars. And that's a lot of stuff. Our star, our sun, has something like 15 planets. So you could multiply this number by 15 and you know, have some kind of estimate for the number of planets that might be out there. And there's just a lot going on. We group these stars into constellations. I talked about that on the planetarium software video. But you know, Cygnus looks kind of like a swan to us, so we tell that story and as a way to remember that. You got the Big Dipper with the handle and the cup, and you've got the Little Dipper smaller. It's got a handle and a cup, a little bit different shape and whatever. I don't think I said anything about this last time, but the Big Dipper and the Little Dipper are in the same part of the sky. They're both in the northern sky. In fact, this is called the Polaris, the north celestial pole is real close to that. But one nice way to find Polaris is to trace these 2 stars and just keep coming. And so I tried to kind of put that where it roughly did that. But in the night sky, you could draw a line between these pointer stars and just go straight up and end up at the tip of the Little Dipper, which is that Polaris. Cassiopeia, Leo, all those constellations that we've already talked about. That's for our convenience. Just because these stars look like they're close together doesn't mean that they actually are. If you had your friend standing talking to you, and right beside your friend, you can see a building, right? If you look just off to the right of your friend, there's a building there. Doesn't mean that the building is right beside your friend. It could be half a mile down the road, right? And these stars are kind of the same way. From our point of view, these are grouped together in the sky. But this one might be 80,000 light years, and this one's 2 light years, you know, much closer. Well, not that close, but you know what I'm saying. Just because they look like they're side by side doesn't mean in the 3rd dimension that they're anywhere near each other. Here's a map of the constellations. You can see that there's those lines running across it. The ecliptic is there. It runs through Leo and Cancer and Gemini and Taurus and Aries and Pisces, like that. You can see the Earth's equator extended out through space. You can see that those cross right there. That's the equinox day, where you know, we move from summer into winter, the summer into fall. And You can see that they've set up the magnitudes of the star there. The brightest stars are 0 magnitude, and then the next brightest stars are 1, and it goes, as the number gets bigger, the star is less bright from our point of view. Okay, so it's kind of a weird number. They've marked some planets right here. This little funny symbol is, my eyes are too old for that. I think it's Saturn that's sitting right there on the ecliptic. So those planets would follow that line. The sun follows that line. The moon follows that line. Anything in our solar system is going to track along right there. All right. The Milky Way kind of runs this way. You can see the thicker band of stars there. So anyway, map of the constellation. It's good to get one of those if you're interested in stars, and you can turn it the appropriate direction. A lot of them come with an outer band that shows the month and the day and the time of day, and then you can spin the sky to line up with that. So you can hold this piece of paper in your hand and know what you're going to see at 10 o'clock tonight. It's kind of neat. Anyway, here's another map. This is closer to home. We've got the sun in the middle. The Earth makes that circle around the sun like that. And you can see how on the small scale things are going to change, right? When Earth is right here in May, we look across and the sun is going to be in Aries. But in January, we look at the sun and it's over there in Sagittarius. Now, we talked about these constellations because those are the constellations of the zodiac. They are the constellations of the zodiac because they're the constellations that the sun passes through. So a long time ago, somebody ascribed importance to that. But like we said, they're all off because of the precession of the Earth. I was born here. When I look across, I see Aries, and yet I'm told that I'm a Taurus, right? So they're all shifted since the creation of that system. I guess in another 20,000 years, I really will be a Taurus, but right now it should be an Aries. Anyway, exoplanets. These are planets that go around a different star. Now, again, when I was in school, nobody knew about any of these. I'll show you in a little bit how we find these and measure them and know anything about them at all. But technology has gotten to the point. Remember how Galileo got a hold of a telescope and found some new stuff? Well, we've got some new telescopes now. We've got some new technology that enables us to find these things. Planets around a different star, extrasolar, outside of our solar system planets. And as of October 22, there are 5,200 of these things that we've confirmed to be. There's another 9,000 that we say, pretty sure that's some more exoplanets around different stars. And here we've got something like 4,000 planetary systems. So you can see if we found 4,000 stars that have 5,000 planets, then we're seeing about 1 or 2 planets per star right now. Well, that kind of makes sense. If you looked at our solar system from a distance, you'd probably see Jupiter and Saturn, right? And the Earth and Mercury and Pluto, they're all too small, too dinky to notice. So it's not really surprising that you're seeing 1 to 2 stars, 1 to 2 planets per star outside of the sun. My guess is that there's, depending on the size of the star that these things are going around, ours has 10. Why shouldn't theirs have 10, or maybe more, or something less, or whatever? But that's an interesting thing. Will we ever get to any of these? Well, we can't get back to the moon right now. We decided we didn't need a space system and scrapped it and just hire the Russians or Elon Musk to take stuff to the International Space Station. But we've sent rovers. We've sent little robots to Mars and Mercury and past Saturn and, throughout the outside of the solar system, actually. Back in the 70s, we had the Voyager program. But I don't know that, I don't know where that's going. Right now, all of the space exploration is done by private citizens and private companies, and at least in the United States. And so I don't know if they'll ever get to, you know, Mars would be a stretch, but we could do it. Will we ever get to any of these? We'd have to come up with a new propulsion system, something that would take us there much faster, or have a spaceship that would allow generations and generations of people to travel in order to get there. We'd have to have a pretty good reason to go, but we'll see. Here's a little bit of information on how they actually find exoplanets, planets around a different star. Possibility one, you take a picture with a big telescope. So here's some telescopes on Earth. These are some telescopes in space. The advantage to using a telescope in space is you're outside of the atmosphere and you don't get that air and the water vapor and the hazing that comes. You get a clearer picture when you're out in space. But we know how to correct some of that from Earth too. So possibility one is to take a picture with a big telescope. The direct imaging stars are marked in green on here. So these are the only direct imaging stars that we found out of all of these. You can see that the planet mass goes up this way. So those are big honking stars that we got a picture. That makes sense. The bigger the star is, the more likely it is that we can actually get a picture of it. I'm sorry, the planet, not star. Most of these are either red or blue, which are either radial velocity planets that we found by radial velocity, or transit by watching them go across. So let me tell you a little bit about that. Radial velocity is measuring the Doppler shift of starlight. You know how when a fire truck comes towards you, the pitch goes, and then when it goes past you, it falls back off again? That's the Doppler shift, and how that changes sound. Even a car will do it kind of like that. There's a change in pitch as the thing moves relative to you. Well, as a star is here, and as that planet is moving one direction and then comes back around as it's moving towards you, this is kind of like the police car coming towards you, and the pitch goes up, and so you see a little bit different frequency of light coming at you, whereas when it's moving away from you, then that's going to take it down a little bit. And that Doppler shift right there is one way to find those. Again, those are the red dots up here. So you can see that the red dots are really good at finding big planets, exoplanets, but they're also, you know, getting down here pretty good. Now the next way is transits. Whenever a planet, when the disk of that star's solar system is lined up to where we see the planet actually cross the surface, where it transits the star, where it comes across, we'd have all of the starlight when the planet is at point 1, and at point 2 it would start to dip, and at point 3 it's gonna block some of the star's light. So as we measure the star intensity, it stays here, and then there's a little dip, and then when the thing moves on off to the other side, it goes back to the first level. So watching the intensity of light coming from individual stars is a really good way. A couple of these guys, the Kepler spacecraft, for example, does a lot of that, looking at stars, trying to find new planets. Microlensing, we could have a star with a planet, and as light from an even farther star comes over it, it could bend that light and change it. That's kind of complicated. You only see a couple of those in here. So that's not one of the better ways, but transit timing variations. If the star has a little bit of periodic motion, see how this star right here actually wobbles a little bit? Well, our star wobbles a little bit too, but if you see a change in that periodic motion, then something's pulling on the star. That something almost certainly has to be a planet, something big enough to wobble a star like that. So that's that. Now, I think this is the last thing that I have here. We've talked about these exoplanets. We've talked about the 3 times 10 to the 24, or I think it's bigger than that, 26 stars out there. If these things do have extra planets, is there anything interesting on that planet? Is there any life on Mars? Was there ever life on Mars? and all these exoplanets and stuff. So there's a whole branch called astrobiology. And these are the questions that they're interested in, kind of, if there's life out there, what would it look like? Well, to do that, you really kind of have to define life, right? What is life? And you say, well, life grows, it repeats and copies itself. Well, fire copies itself, fire is going to grow. So you got to be careful with the definitions of what life is. Is bacteria life? Is a virus life? Usually we don't consider a virus life, but bacteria is, So there's some nuance there that you have to work your way through. But once you've kind of got a working definition, how does life originate? Again, that kind of goes back to cosmology and everything. How does life evolve? We're a carbon-based life form, right? We've got carbon molecules in us that make life possible. Is there another system? On Sakwat 904, could you have a silicon-based life form instead of carbon, right? That would be a different kind of life. What would that look like? What kind of environment do you need for life to survive? We have to have oxygen and water. Could another planet that doesn't have oxygen or water, could there be life there? We are seeing some oxygen in other places and water vapor and stuff, but what if it's not there? Is that just shut the door on life? What would it look like? Has there been life anywhere else on our solar system? There's a moon of Saturn that people are really interested in because it's got this big ocean on it. And there are people that would very much like to build submarine rovers, robot submarines that we could send to this moon and have it dig down through the ice into the ocean there and poke around and see what we find. Is that worth doing? I don't know. We need to solve some problems here on Earth, but this question, are we alone in the universe, is pretty compelling. How do we observe a habitable or an inhabited world? What's our future on Earth and beyond? We already are at the point where these forever chemicals make it so you shouldn't eat the fish that comes up out of the river, and won't be long till it's in the plants and all the food that we eat and everything. At some point, we have polluted this place to the point where we can't, live here anymore. And what do we do then? Is there another place we could go? So this astrobiology kind of ties into that, and in a long-range sense might be an important question one day. I did want to put this picture up here just for fun. This is called a tardigrade, or a water bear, moss piglet, or 3 different names. This is a little animal that lives here on Earth. It's a little 8-legged thing, and it's microscopic. It's a little bitty thing, but this guy right here is just about unbeatable. You can freeze these guys. You can send them out into space where there's no oxygen. You can put them in an oven and dry them out and turn them into powder, and then you put water on them and they pop back up and they're still alive and stuff. It's a very different kind of life than anything else that we're used to seeing. That's here on Earth. These things are everywhere. And so life is one of these things that just pops up, and it's whose place is it to say, well, everything should have 2 feet and be between 5 and 6 feet tall and have 2 eyes and a mouth? What is it that what counts as life? Even if we could find bacteria on Mars, that would be a counterexample. That would be a way to say, yes, we have found life somewhere else other than on Earth. And that would be a big deal. My guess is that there is life on other places. And there's no reason to think that we are the only people, the only place where life has ever existed. But we'll see. It's an interesting question. Well, thanks for stopping by today, and that finishes up the astronomy stuff, and hope you have a great day. Thanks.